Okay, hello one more time. I am happy that not only my face is so fresh and happy today. So we have one practical session, one for me and my colleague Yaroslav, and the idea is next. After me, Yaroslav will talk about some three state-of-the-art model which was mentioned multiple times during this school. I will not tell the model name, and I will talk a little bit some tips for working with time series. We'll share one package which I use for research needs when I need to process something serious, test some hypotheses, and other stuff. Okay, who has some experience with time series in the context of forecasting? Okay, which tools do you use for that?
It's simple ML models and the profit from that.
Okay. From which packages do you use that?
Usually.
Profit maybe higher price.
I just used staff models and specific for spectral analysis that you wanted to do.
Okay, so there was mentioned stat models, which is the old one. Top hat from Meta. I don't know how to pronounce this model, but it's really powerful. Anyway, scikit-learn. So what about some data preprocessing? Because, for example, when we have a multiple time series and we need to apply some rolling windows feature engineering, some logs, and other stuff. Okay, good. That means something that I will show can be valuable. Let me share the Google Chrome. Huh. Okay.
This page.
Okay. So, like 1 or 2 years ago, I found Nixla, that's some kind of ecosystem for working with time series for forecasting and analysis. And today I will just share some tips from my experience when I use this ecosystem. What I mean by ecosystem is like a group of packages for different needs. There are one of package stat forecast which aim to work with statistical and econometrics model, ML forecast, which is some kind of extension to use classical ML models for time series forecasting. Neural forecast, the same for neural networks. And multiple for other needs. So let me describe the first thing. It's a time GPT. That's one of the first transformers which was made for a time series forecasting, and it's now available on Azure. So, like, I guess 1 or 2 years, maybe 2 years ago, the Nextcloud team created and trained transformer based on time series from different domains. So I checked that. That's interesting, but it's not open source. And I didn't find any practical usage of that. But if you are interested in transformers for a time series forecasting, you can check that. And also after Time GPT, they released multiple transformers for time series forecasting on the Hugging Face, which are open source. You can also try that for modeling. The second package is Stat Forecast. That's also library which contain really a lot of models, which is available through Python interface. Maybe the people from the old school which use R for programming, like a few years ago, they can say that Python just do not have this diverse number of models and visualization packages that Python has. That was about some ggplot visualization on R, and also it was the same for classical time series models like ARIMA, AutoARIMA, and other stuff. So stat models, that's one of the alternative to use ARIMA-like models. This always is autoregressive variants. Not in stat models and not in R. That's also one of the alternatives. Also, there exists AutoARIMA, which optimize hyperparameters with Akayeki parameter. But anyway, another one is ML forecast, which I will show in a collab how programming interface look like. So we'll skip it and check in details how it looks like. Also, there are neural forecast where you can apply for a time series different neural networks architecture for a time series. I didn't work with that a lot, to be honest, but if you like time series for a time neural network for time series, you can try it as well. So also there are a lot of extensions which can be useful as well. For example, there are predefined data sets for sales forecasting, Favorita and M5 from the Kaggle competitions, if you know. So for fast experiments. Okay, I will move to the collab to show how the programming interface looks like, but maybe you have any questions about the idea of this library.
So this is like a library that has all of these models. Right?
Yeah.
Mm-hmm. That's interesting. Is it open source?
Except TimeGPT.
Okay.
Also, before I move to the collab, from my experience, this library is good for first steps experiments, I guess. I'm not sure about the production use of this library because sometimes it's not clear, and last 2 years it was really dynamically developed. So yesterday when I prepared a collab and I tried to reuse some of my old code, it just didn't work. So that's one of the things that you think about before thinking about deployment to the production. It's more research ecosystem, I guess. Yeah, you check question.
How is it like accurate model? So putting, so it's not production ready. No, like.
That's just, on my opinion, it's not like code base is not a stable SA1. It's really dynamic, but from the last releases, I see the better programming interface for the inference. Before it wasn't stable.
But use like a proprietary, like some inertial types of data classes that you use.
Yeah. It's really want to predefine the data frame, but let me show how it looks like. Okay. What I did, I took one of the good tutorials from the ML forecast part and use a data set for a hourly electricity load forecasting. So you will be able to check the full data set. Okay, we can skip it for now. So I use a predefined by this library data frame, but generally, as you ask, this library wants this format of a data frame before modeling. So unique ID, it's an ID of a time series. For example, if we work with sales forecasting, it can be SKU. It's like unique ID, that's idea of time series.
Can there be multiple time series interacting with each other?
Yeah.
Like, why do you need this ID to distinguish between different time
series? This idea is needed to work with multiple time series for a same model.
And so they like same model works with multiple time series.
Yeah.
Okay.
For example, you can run LGBM on
I don't know.
100 time series.
What is LGPM?
Light boost. It's like a booster model.
Okay. Thank you.
DS, that's just time, daytime, and value on that day. Okay, in this example, we use only one time series, but you can experiment with a multiple. One of the good stuff that it's contain a lot of predefined functions. So if we have a typical structure of data frame, we can have a typical functions. For example, for this case, we can just plot a data frame without any additional processing of our data frame. And also, as it built based on a matplotlib, you can customize it with matplotlib as well. So what we do before we start modeling, we make some kind of train and test set splitting. We just remove for testing last 24 hours to make evaluation on last day forecasting. Okay, I don't like this function, to be honest, because it's huge. You can skip that, but you can figure out with that better. Okay, how modeling looks like. The programming interface use ML forecast class where you can define a models which you will use. This model can be just a simple model from the scikit-learn, like linear regression, decision tree regression, XGBoost. Also, it can be external machine learning libs like XGBoost, LGBM, and other stuff. Also, we need to define frequency. Like for our case, it's hourly. Sometimes it can be daily. And also, we can transform our target. In that case, we just make a difference to remove a trends from our data. Yep.
Regarding the models list, will it like make an average of the results, or it will choose the best on how it works? Is it like ML forecast is a framework?
Yeah, it's a framework. I will show how it works with multiple models.
What does target transforms do exactly?
We make differences to this is one of the approach to make time series stationary.
Okay. So
how to call it in English?
yeah, so stationary.
Station.
So you difference the time series and inside of the ML forecast object, what does it do? It just creates two different instances.
That just transform our target. For example, here we have.
Okay. So this is like a consequence of difference.
Yes.
So it applies to them.
Yeah.
Okay.
Yeah, that's like a difference on the lux.
And the units there are hours because we specified that frequency is hours.
Yeah.
Okay. Thank you.
So we can make plots after our basic processing. So let's move to the modeling. As I said, we can use the models from the scikit-learn. We can use external machine learning. Also, there are a lot of functions for transformation, like with expanding windows, with rolling windows features, with differences. If you work with time series, I guess you know meaning all of that. Also, you can make some custom models. For example, naive, we just return a previous naive model returns the previous value as the inference, just for baselining. So we create a list of models which we will try to use, and the same. So current here in ML forecast class, we init our models list. We mentioned that our frequency is hourly, make our target transformation, which was showed before, mentioned some blocks, transformation for blocks, and also we can add date features. And if we work with a multiple time series where we have a different features, for example, for sales forecasting, where we can have some SQ groups, we can have some features like weights or other stuff which can be used for commodities. Yeah.
Okay. So we define lags. So we define like that. For example, the naive model looks at the column lag 1. So the data set will have 3 columns, like lag 1, lag 12, lag 24, right? Which will be 1 step behind, 12 steps behind. So 12 steps behind, 24 steps behind. Then we apply a transform to each of them. Why do we do this? So we apply to 1 and 24, expanding mean, rolling mean. What does it mean?
Okay, that's just for feature engineering, because in the context of ML, this will be our target, and all of that will be our features as the input.
I see. So you basically, with these two plus parameters, you added additional columns. One of them,
additional features.
Yeah, additional features. One of them is just transformation of lags. The other one is month, hour, and day week. Okay.
Yeah, but you can play with that in a different way. Can be like 2, 3, 4.
And so, like these day of week and month and hours, you define somewhere in documentation, right? It's keywords.
Yeah.
Okay.
All of that is mentioned in the documentation. And to be honest, in the context of working with feature engineering for expanding and rolling windows, it's really difficult by only working with pandas. So it's better maybe for production, but when you just experiment and wants to check which features is important, it's really easy to use.
Okay, thank you.
Yeah, and also you can add additional categorical features and numerical features if your dataset contains that. Okay, so we made some feature engineering for our time series. And after that, we can do fitting. And one of the options is to make a cross-validation. I hope that everyone remember about cross-validation from the first lecture. That means that we select in this case, 4 windows where we make like modeling on a window and make inference for this window to evaluate on a train set our modeling. So H it's that's mean forecasting horizon. As you remember, we took to the test set last 24 hours for the inference. So we trained our model for 24 hours for the inference. So we put the train data set, forecasting horizon, number of windows for cross-validation. And yeah.
So how does cross-validation work if we only have a time series? Does it like extract a period of time from the middle of it or something?
Yeah, maybe.
So, but extracting from the middle will reduce the amount of training data.
Yeah.
Okay.
It's mean like we have. Okay, we work firstly on this part.
Okay. So you split the time series in 5 parts and 4 parts.
Yeah.
And for everyone, you take the last 24 hours. Okay. And they don't also say. Okay.
Yeah, but it's not like on a classical machine learning when we randomly select 4 or 5 subsets and run on that. We take into account the time switches. So the result of cross-validation is a data frame where we have a unique ID as a unique identifier of time series. Our date time cut off its a starting point of our window. So if we make so if we make a call of unique function for a cutoff column, we can see that there are 4 starting points as a number of windows. So cutoff, that's start of our window. What is next? Next is our real value. And after that, the value which was predicted for each model for exact date time. And by having this information, we can calculate some metrics for our train set. And before do that, we can also make a plot. Okay, I will do not analyze this function. What we do, we have 4 time series with visualization of a prediction. These 4 series, it's our 4 windows. And we're checking for each window with the result of forecasting. So, and the next, what we can do, we can also run some evaluation. And this library also have most of the popular metrics for regression evaluation. And by running our evaluation for a trained set, we can see that naive model perform badly. Like GPM is the best one here. So we can make some error analysis and other stuff. And let's talk a little bit about inference. So I was surprised that ML forecast added a programming interface for predict intervals. So we took like GPM and Lasso model to make inference. So what we do that here, we also reinitialize our ML forecast flow and just feed on the whole data set our model. Just do not only do cross validation for experiments. We feed our model. Also, we can define some levels for the evaluation quality of models, getting the result for a model and each level for the model. What we do next after getting a forecast, we are also join our forecasts on a test set just to get the whole data for the evaluation, and we get the for this same series, which we have only one, we have such metrics.
What is levels again? Previously.
The Virch interval.
Again?
The Virch interval.
Ah, okay. Confidence interval.
Yeah.
Yeah, okay.
Sorry, I learned the statistic in Ukrainian.
So you just predict the confidence interval size for 90% or 95%.
Yeah, make evaluation, and also we can make a chart for our forecasting. So I guess that's it that I wanted to show. I deal with Yaroslav to have 30 minutes. But yeah, do you have any additional questions? I hope that these libraries can be helpful to you.
Why didn't you try Sarima on the electricity data?
You'll need to price your
First of all, I wanted to show how we can put ML models for the series. So to check Sarima, I needed stat models. Generally, stat models has a pretty similar programming interface, but also there are some tricky moments in that I don't like with Sarima, Rima, Arma, and all of these regressive models that there are a same programming interface, like same class, Rima, but in the parameters, you suggest which of the option of the Rima you can choose. So by adding the seasonality, this class Rima becomes Rima. By removing some integrational option, Rima become Arma, and other stuff that must be taken into account when we use this Rima family models. But yeah, it's also can be used here.
Okay, another question is, you have 5 cross-validation splits, and each of them has 24 hours, but this means that the test set is only 3 days, wait, 4 days, sorry, out of the whole training set size of 3 years. So like 4 tests only on 4 days, so this is not a lot to test.
Yeah, that's true, but that's just example how it can be used. Because as I wanted to show like multiple models, I will wait a lot to test on the number of windows. Yeah, but also must figure out in details somehow, because I feel that I do not fully understand the logic of cross-validation splitting in this library.
So like in reality, can we take like 80% for training, and then the last 20% we just run it multiple times there?
Yeah.
So first 24, then.
Yep, it can be implemented as well. How it can be done when we need the ML forecast class for the training, we just feed on the whole train set, not making a cross validation. And after that, we can just make we can make a prediction on a test set.
Yeah, but I meant like you, for example, you leave 100 days, you predict the first 24 hours, then you add 24 hours to the input, predict the next 24 hours.
I'm not sure if it's customizable in this way, but I guess it can be done.
Yeah, just yeah. Thank you.
I guess there was also some questions.
On the cross-validation metrics, we saw that slide GPM is much better than the lasso, but on the test data revised. The lasso is better than my GPM. Why that may be so?
What are your insights about this?
So if we have a better score on a train set, but worse metric on a test set, what does it mean?
But that's cross-validation.
Okay, worse. That means that we have some kind of overfitting here.
On the cross-validation.
So LGPM is overfit and lasso is like perfectly boosted.
Well, in the context of time series, it can mean that this time series може бути heteroscedantичним. Heteroscedasticity, that means that our statistical features of a time series changing during the time. And while we have some statistical features of our time series on a train can change on a test set, that means that we cannot use more complex model, which will learn all of these dependencies. Maybe we need a model which generalize better, like some linear models. It's like maybe less quality prediction, but more stable. It's some kind of trade-off. Also, I read an article which was published in April this year, and the question here was if better quality forecast for a sales forecast will optimize the spends for the logistics. And the author made a simulation, and it shows that we need just a simple linear model which will generalize it better, and there are more dependency on your logistics systems than on a better forecast. So when we talk about forecasting for decision making for business processes, it's better to think about it complex, because we are working in a complex system, not only about simple forecasting metrics. It's some kind of reductionism.
Well, to also add that LGPM is very finicky with the feature selections that you give it. If you give it features that are not important, it generally impacts the performance. And with Lasso, it probably selects features better, and if a feature is irrelevant, it doesn't affect the performance.
Good hypothesis. As Lasso is linear regression with normalization, so it's good hypothesis. So I guess I can finish. Anyway, I'm available to talk about time series, which I really love after the lecture. Yaroslav, I guess you need to join to the Zoom. Okay. Hey, welcome, Yaroslav. Oh. І це ж у нього. А, не працював? Окей.
Can you send the link to the collab?
Yeah, I will send do you want it now? I don't think he will run it, or he will not be able to run it as of now because there are some issues. Basically, today we will talk about one specific model that I think will be interesting to you. It was released, it was released like a long time ago, but then it was improved, and there's this third version that came out 7 days ago. And I think a lot of teams kind of talked about this, so I think it would be useful to kind of generally understand and see what it does and what it is. Just let me set up the screen so you can see it. Let me know if this is okay, or should I zoom?
Zoom, please.
Should we also turn out the lights?
And make sense mine.
Is this better?
Okay. Maybe we can tell them what the future means. I know that well supervised. Is it like trained to be multimodal on textual data or only visual? Like, can we use sound, for example?
Yeah.
Audio range.
Not specifically for this model, but if you train, yes. We'll also take a look at the picture, so you can I hope you can grasp the idea of this. But generally, today I wanted, so this is kind of, I know that you are all into the projects, and I wanted to kind of have this session more of a visual kind of style. So I think we'll just go through some images to see how the model works. And the model we are going to talk today, well, one of them is Dino V3. So this is the third iteration of Dino models, which are self-supervised models for image understanding.
Did you send this to link?
I can, but still, you will not be able to run it right away.
Okay.
So, okay, just give me a second, I'll send it.
Okay, thank you.
Okay, so the link is in the chat. You should be able to open it and follow the images. Okay, once again, let me show the screen. Okay, we can start. Basically, again, what this model is about, it's about self-supervised learning, basically to understand images and what is on the image. And they also have integrated into the Hugging Face ecosystem, so this is nice and it would be quite easy to load the model itself. So all we need is what is called auto image processor and auto model. That will kind of read the config file of the model itself from the Hugging Face repo, and it will basically load the model itself. And one thing is image processor, which what it does, it basically takes an input image, and it normalizes it, rescales, resizes. So this is like a pre-processing step. And then the auto model basically will load the Dino V3, and we will be able to do all this in the pipeline for processing the image. Yeah, so basically you have the token here. Okay, my bad, but I will deactivate it. But anyways,
So what we will look into is the DynaV3, which is a vision transformer model. It was pre-trained in several kind of data sets. One of the data sets is basically satellite images. And I think this is very important because, as they mentioned in the paper, they have this really, really cool figure where they kind of show what the model is capable of. And one cool thing about the model itself is that it works on pretty large scale images. So it means, and also the model itself wasn't trained to wasn't trained on such scales. So if you upscale the image, the model is able to understand that scale. And they also, so they have two kind of iterations of training. One is pre-training on kind of regular images from one data set, and then the satellite images. So in this example, we will use the model which is pre-trained on satellite data. There are several variations of it. And the only problem with this is if you want to access the model, you kind of have to fill in the form. And so on the side of the meta team, they have to confirm it. So then you will be able to load it. But yeah, anyways, so let's kind of recall the transformers and basically get back to the question whether the multimodality is possible. So if you recall, what is the first step for kind of doing the transformer, or what is the input to the transformer, or what the transformer works with, are basically tokens or embeddings. And the thing is, as you kind of recall from what Raul's lecture was, we have an input image which we want to divide into kind of squares, patches. And then we project those patches, or we flatten them into a sequence of pixels. And those sequence of pixels can be then linearly projected with learnable linear projection into a d-dimensional embedding. And so each of the parts of an image, basically patches, are now represented in this high-dimensional space. And then this is what the transformer works with, basically embeddings, bunch of numbers, basically vectors and numbers. And there's a lot of
Other patches are just a grid, or there's like a region of interest?
No. So you kind of slice up the image entirely. So you have some number of patches, and each patch is some sort of information about the image. And then the model kind of learns that maybe this patch of a face of a dog is more important than some background patch. Yeah. And basically this happens through attention mechanism, which is inside the model. But basically what I want you to understand is that the model itself works with vectors, basically embeddings that we have. And about multimodality in the case, we can actually take any kind of modality or data that we have. Is it whether it's image, whether it's text, whether it's audio? It actually started with text when we had NLP breakthrough with transformers. Then it moved on to images and then to audio. And basically anything you can tokenize into a vector, you can project into a vector and then use it with transformers. And the multimodality comes with kind of integrating contrastive learning, training or pre-training with multiple modalities. So the model kind of understands what happens, basically the relationship between text embeddings and image embeddings. So this is an essence of a transformer, and I just want you to understand that we work with those vectors, which are basically embeddings, what we call them that. So now about the area of images. So there's a function that also, this is a library from Hugging Face again. It's called datasets, which basically loads any dataset that you want from the Hugging Face repo. And so we will use some sort of satellite images that is the dataset for segmentation of different parts or different regions on those images. I hope you can see the image itself.
Yeah, we can.
Okay. So we will be working with this example, this specific one of the field. And what is the first step for us to do is to run the model through the processor. Remember the thing that kind of normalizes our image, resizes it. There's a kind of standard baseline or default image size. So it's 224, which is what the vision transformer is pre-trained beforehand. But we can actually scale, the image itself whenever we want. So we run the inference on the model, and we basically get the output hidden states, which are our embeddings. And what we can actually see when we kind of reshape the stuff, we can see that the model itself, it outputs this shape. So there are 32 by 32 kind of images, which actually have a lot of channels. So 1,280 channels specifically. And this is a lot, actually. And what this 32 by 32 is the number of patches. Why? Because remember that we got this image. The processor by default resized it to 224. And actually, it resized it to 512 in this example. But then we had a default like size of patch, so 16 by 16 pixels. So this means that we end up having 32 by 32 patches, like an image. So now what we can do, we can actually visualize what the model kind of processed it. Because again, what the model is supposed to do is supposed to take an input image and understand it. So basically, there is a semantic meaning of different parts of an image that the model kind of connects and understands. So what happens when we visualize, for example, first channels of what the model kind of thinks about the image? And this is what we had. Basically, there are some patterns we can see. So remember that we work with this field. We can actually see that the model kind of understands these patterns. And what is cool is that we can actually recreate what's in the paper. So remember how we got those colorful images? And just to recall what those images are. So we have an output from the model, which has a lot of dimensions. So it's a really long vector. A sequence of really long vectors. And what we can actually do, we can actually use a PCA. Basically, linearly project our embeddings into a lower dimensional space, specifically 3-dimensional space. Why 3? Because we want to get RGB kind of numbers for each specific patch. So with these 3 numbers, we will be able to plot the RGB image. Yeah, basically, there's a code. I think you can also run it later, but basically what I want to experiment with is actually changing the resolution of an image, just to show you what the model is capable of. So for example, we start with some low number of patches, or the low number of or small image size, basically. The model, what it outputs is basically for each patch, so like each breakpoint on this image is a 3-dimensional vector, which is an RGB channel at this point. And this vector was projected from this high-dimensional space. So basically, what I want you to understand from this image is that model actually understands what's on the image. So if you have this kind of region of a field of some sort of concrete, the model colors it with pretty much the same colors. So it's like green, bluish, etc. Then there's like more yellowish colors, which are trees actually. So the model kind of gets the idea what the trees are on the image, and everything is pretty much blurred out in this purple color. But what happens if we, let's say, increase the model size by a factor of 3 and run the code again? So again, the model wasn't trained specifically to do or process large image sizes, but inherently it was kind of pre-trained to do this because it was trained on different number of or different sizes of images. And on inference, model can actually, so they saw that model is capable of kind of understanding deeper semantics of large scale images too. This is what we got. We got a more refined image, or a more refined embeddings of our input image. And you can actually kind of start to see the line of trees, how it looks like. And we actually can increase the size even more and run it once again. So let's do it for a scale of 4. So basically, the model with scale number of pixels or image size, the model can now process and understand more patches, which means more resolution to the image, which is very important if you want to get very high quality embeddings of your image. So it will run for a bit longer than previous models or previous images. So we can wait for it, but still, the model itself is very cool, and it seems to be very, very cool compared to the previous model, because now it understands the relationship. So it was trained in a way where it kind of understands that it needs to have quite similar embeddings for its neighbors at each point. Okay, while it's running. Okay, so basically a more refined version of what we got before. If you look closer, you can kind of see there's a pattern of those lines. Basically, the white lines that are on the parking spots, they start to appear. But now, what is important? So we have, for example, this, and what we can do with it is the main question. Well, in this notebook, you will also find not only the PCA projection, but the UMAP projection. You can also go through it. It will get you a little bit of a different kind of image, and but still, this is a projection to a lower dimension space, so nothing really fancy. Just with not like the linear projection, but a UMAP projection. And basically, with UMAP, what is cool is that if you run it and kind of plot where the embeddings are located on the 2D grid, not the 3D grid as we previously did, we get this image. So what is cool about the UMAP is that if you look at the image itself, only what it does. So it kind of tries to recreate the topological structure of high-dimensional embeddings. And how are they in relation with each other in a low-dimensional space. So this means that it kind of creates a graph in high-dimensional space and tries to optimize the graph to look quite similar or have quite similar neighbors in the low-dimensional space. So this actually, what I mean by that is that for each close embedding, or the embeddings which are close in the image will be also close in the projection. So you can actually kind of see that there's a gradient pattern going from red to purplish, something like that. And now if you take a look at this image, there's a lot of mass going on, but I think there's a very cool one pattern that sticks out. And specifically, let's take a look at these four sticks on the top of the image. So what this actually means is that there's something that model actually gets, which is not the part of a bigger thing. And I think I was also playing around with it, and I thought to myself, what can it be actually? Do you have any guesses maybe?
The fields.
So we have this image, and we have these four, or maybe this is fifth, I don't know, maybe fifth part.
5 fields.
Then that's a good guess. And actually, if you want to test this out, what we can do, so basically right now we don't understand what this map is, but what we can actually do, and this is one cool thing. So we can actually do a segmentation on features which are outputs of the Dynamo model. And the way we do it is by using k-means, which is a clustering algorithm. We can actually initialize it with any number of k clusters that we want, but in this example, we will use six of them. And we will run the algorithm on these high-dimensional embeddings, basically. So the 1,280 numbers, which means something for each patch, will get clustered into 6 different groups. And with each group, we will basically we'll mark it with a specific color. So what happens is that colorful RGB map, which we had projected into 3-dimensional space, which was previously in high-dimensional space, is now colored. And it's now basically segmented. So each specific pixel on the image is a segmentation number, starting from 0 and ending with 1, because we have 6 clusters. You can actually see how the model gets this stuff. So it gets that there are trees which are blue. There's also this forest area on the top. It gets these 5 fields. It gets the road, it gets the dirt, it gets the grass and stuff. So basically, yeah.
So this comes from the UMAP, dimensional reduction.
No, the UMAP is separate. So what we did, we took the Dynamo, bit the image, got the embeddings, and did the k-means clustering. That's it.
This is not.
And yeah, I just wanted to show the UMAP example as a way to understand that you can actually color the UMAP based on the segmentation that you have. So basically, each point on the UMAP now represents the same color as a segmentation map. So now recall that we have discussed this idea was kind of having these four sticks, which basically stick out of the general graph that we got. And actually, if you take a look at the color, so it's kind of cyan color, it's actually the fields, basically the parts which are contoured. Yeah, there are actually a lot of cool stuff that we can do with the model. For example, we can prompt some specific embedding in some location and see what similarities we get with the other embeddings. So this is kind of shows if the model actually has, I hope you can see the red parts. Basically, if we take, for example, this embedding here, we compare, we could calculate the cosine similarity with each and every single one of the rest of the embeddings. And we can actually see which embeddings or which parts are similar, which patches are similar. And they are highlighted in more in this more brighter color. So basically, if you try to prompt it, we can see that the model actually gets that. If we highlight or we mark the tree, it gets all the trees. If we highlight the field or the contour, it gets the contours. It gets the grass, it gets the road, etc. So this is another cool application which can be used. Apart from that, we can actually do something even cooler. We can actually try to do image matching. So imagine that you have an image on the left, this one. And then you try to understand whether this image has something in common in terms of embeddings, and similarity about embeddings, with this image on the left. So actually this image, image on the right. So the image on the right is actually a crop from this specific region of the first image, but it kind of shows you the idea. So this is not exactly how matching algorithms work, but this actually shows you an idea of kind of feature matching that we can do out of the box without needing to train anything. So the model itself is kind of capable of doing that because it gets the similarity. So it does understand that kind of this feature is very similar to this feature. And then we visualize here, I think it's 100 top selections. So 100 top sign similarities between embeddings.
Do you have the probability of the similarity for each like point pairs?
Yeah, so we compute it. So we have basically two images, and we basically compute each embedding from this part with the embedding from this part.
Okay.
Yep.
So you get all this from single run from different, right?
Yeah. But basically two runs, but you can think of it as one run if you can, because this is the same image. But essentially you have to process two images, and then you have embeddings for those, and then you can compare.
So basically, like all you've shown before, this was like your job, not the models. Like the model calculated the embeddings, and then you like.
Yeah, so model only outputs the embeddings or the combined embedding, which is kind of pulling or averaging all the embeddings into a single one, which you can then later use for classification, for example. But having also a kind of grid or the map of embeddings is also useful for stuff like this. So again, remember when we talked about that we had an image where there was a plane and a bird, and the model kind of matched the wings of a plane to the wings of a bird. This is exactly why it does it, because it understands the meaning of stuff. So this way of matching is not the best way because the model wasn't trained to do that. In a sense, if we would have very repeating pattern, we would not, so the model would be confused because there will be a lot of similarities which also have high values. It doesn't understand the location or kind of a lot of what is happening around maybe. But generally, it does a pretty good job. So if you want to match, for example, sequence of aerial images, you can pretty much do it. Or if you want to understand whether, for example, how one image differs from another image, for example, for seasoning, you have kind of time steps, right? For example, winter and summer, you can actually pretty much do the same job and get the pretty much similar embeddings because the model will understand the general structure of the image. Okay. Yeah, so we can actually visualize it even cooler. I really like this map. Basically the same visualization that you got before, but with these crosses. Okay. Any more questions at this point?
So how do you use this in practice? Do you just use this for automatic annotation, segmentation, based on segmentation?
Well, generally the model was trained as a first part to the, for example, in the previous, what they've done, so this is a self-supervised pre-training. And this is called specifically pre-training because then you will later train it on your specific data set. You can do stuff like that just out of the box. But the model itself is meant to first capture a lot of information from the general world because it was trained on a huge data set and the model is huge. And then later you can add on your hats. Remember where we talked about in the first lecture of the CV, the model has different parts. It has the backbone, it has the net, it has the hat, which does the prediction, for example, for bounding boxes or segmentation maps. So what you can actually do with this, you can take the weights or basically coefficients of the model, right? So the model itself. You do what's called freezing of the model. So the weights are not, so they will not change during the next iteration of training. This means that you can add, for example, a segmentation hat and train it on your data set. So the first part, so the big dyno model will not change the weights. You will only change the weights of the segmentation hat. And this way you can actually get very useful features that we saw before. So the model generally understands very good images. And later on, you can actually train the model to do very good job of segmentation. So this is the general use of it, but you can still use it as a out of the box, let's say, annotation, as if you want like weak annotations, let's say. They also look pretty nice. So if you have, let's say, a data set where you want to understand or maybe segment 2 classes or 3 classes, because you kind of know it as a prior, you can actually do it. So you just generalize or just get the 3 Ks for the k-means and run the model.
Okay, thank you. So you can get away with a small data set.
Yes, exactly. That's pretty much the purpose of it. And because this is a huge transformer, and the head, like the head of, for example, segmentation, is usually convolutional neural net. So you don't really, it can be also transformer, but you don't really have to use it. So this is exactly what we need self-supervised pre-training to generally understand the world.
Do we have an embedding for every point or every patch, and how we like upscale from an embedding, for example, for a patch to classification for every point or clusterization?
I hope I got your question right. So basically what we have here is, so each kind of pixel on this map, right now it has a color, right? So it has RGB color, there's 3 numbers. But why we have this image is because we projected what we had previously, so a lot of numbers, specifically 1028, which we got here. This is what the model outputs. We projected those into a lower dimensional space. So we got 3 numbers.
Just for visualization?
Yes, only for this colorful image. But we used all of these channels for k-means to get the segmentation. And your question is whether we can use this segmentation now or segmentation or...
No, my question was, do we have an embedding for every point or every patch?
Well, every patch is a point for the output, basically. So it's like if you scale down the image, remember we had, yeah, let's run it one more time. So we have this
maybe I got it. We have a patch around every point.
No, every point is a patch. So look, here is a scaled down image. So it's like a 224 image, right? 224 by 224, which we inputted to the dyno model. And we got, sorry, I'm confused. So we inputted actually 512 by 512 images, just a bit bigger. And we got 32 patches. Why 32 patches? Because each patch, it has 16 pixels by 16 pixels. So now this below, this is only 4 first channels, what we got from the model. And each kind of pixelated part is a point on the map or a patch on the map, which the model outputs. basically patches is what we get from dividing the image, but these are embeddings.
Okay, we transform the channels to the coordinates of the patch.
How we can get like high resolution, colorful plot of the image below? It's not like those pixel wise.
Yeah, you just need to scale the input image higher because look, why we get this pixelated image is because the model divides the image into patches which are 16 by 16. So we end up having 32 by 32 images. You can count there are 32 by 32 squares. So this is low resolution. But to get high resolution, we need to scale up the input image because it will still get divided into 16 by 16 patches, but there will be much large number of those. And the model itself can actually process those images as we saw before. So this is a much larger image. I think it was 4,000 or 3,000 something. And this is what we get. So these are the colorful projected embeddings. Yeah, and
it's like we have online representations of it's just because like for the location or what we get with the image.
So this one, you mean?
Yeah.
Let's go back to this example. So remember that we got an output of 32 by 32 number of embeddings, and each embedding, so each kind of single point or square, it has 1,280 numbers. Because this is a dimension of each embedding. What we cannot actually visualize it in the RGB channels, right? So what we did, we used a BCA to project each of this embedding vector in the 3 coordinate system to get RGB figures.
So they just visualize like the color of the terms.
Yeah, exactly. So this is exactly what they did in the paper. Maybe with background removal for cats, but oh, by the way, I also have cats. Yeah, so the lecture would not be as good if we would not have also cats. Remember about the experiment that I talked about on the first lecture, which is a secret still. But yeah, still we have cats. So we can actually do projection of cats. We can project them into a 3-dimensional space. And this is what they look like. And we can actually also prompt. So remember these points that we did? We can actually do the same thing. So I would suggest you to play around. So there are various amounts of models. So there is a dynamic 3, which is VAT large, VAT huge, VAT small, basically a large number of pre-trained models on 2 different data sets, LBD and the satellite images. And for the question about multimodality, there is a CLIP model, which was also mentioned in Raul's lecture. I will also send a link to this. Unfortunately, we don't have really much time to go through it, but I think it would be worth looking into what it does. It also has one cool part. So what the model does basically matches 2 modalities, text and images. And one very cool thing that that you can do with this is out of the box, you are able to do localization of objects. So let's say you want to localize where the green apples are, and you kind of prompt the model to localize green apples. It can do this. So this is what the output looks like. Let's go a little down. So this is what the output looks like. You can actually get those into segmentation maps. What happens is you define a window, like a square window, which you slide across the image, with overlap, like a convolution. And for each window, you compute basically the cosine similarity between text embedding, which is a green apple, which we prompted, and the patch of an image. Yeah, so this is cool stuff that you can do with multimodality and dynamic 3 model, and I hope this will be useful. Thank you. Yeah.
Why segmentation?
Like Ціна кав. Ціна кав.
А можете не запитати, будь ласка, QA.